Welcome to the first lecture on limit and continuity. So let's start with the limit point of a set. So here is the definition. Limit point of a set. So first of all, let A be a non-empty subset of R. Non-empty subset of R. Okay. Then a point X in R, that's mean this point X may not be in A. So a point X in R is said to be a limit point of the set A if there exists a sequence, better to write, there exists a convergent sequence, say convergent sequence, say xn in A, that's mean contained in A with xn not equal to x for all n belongs to natural number, such that the sequence xn converges to x. So we write limit n tending to infinity xn equal to x. Okay, that's mean if you have a non-empty subset of R, it may not be an interval. Okay, then a point X, that X can be in A or may not be in A. Then any point X in R is said to be a limit point of the set A if we have a convergent sequence xn where each term of the sequence xn in A, but each term is not equal to x. Okay, and that sequence converts to x. Okay, now by using this limit point of a set, we can define closed set. So first we define closed set and then we shall see some examples. So let's write the definition of closed set. So a set, say a subset of R, is said to be a closed set if S contains all of its limit points. All of its limit points. Okay, so in other words, a set S is said to be closed if for any convergent sequence, so for any convergent sequence xn contained in S with, say, xn converges to x. Okay, then we have x belongs to S. That's mean if we have a convergent sequence where each term of the sequence is contained in S, and if the convergent sequence converges to a point X, then that X must be in S. So if the set A satisfies this property, then the set is said to be a closed set. Now here we have some examples. So first we can take the set is open interval 0, 1. Okay, so first we will find what are the limit point of this set and this set is closed or not. So first of all, you can check that if we take xn equal to 1 by n plus 1, okay, where n belongs to natural number. Now if you take this sequence, then you can easily check that this xn belongs to A, right? And xn converges to where? 0, right? So that's mean, and also we can check that xn is not equal to 0 for all n, right? So that's mean we have a convergent sequence xn, okay, where each term of the sequence contained in A and the sequence xn converges to 0. Therefore 0 is a limit point of A. Now that implies 0 is a limit point of A. Okay. Now what about 1? Now similarly you can check that if we take my xn equal to say 1 minus 1 by n plus 1, where n belongs to natural number, then each of the term xn belongs to A, right? That's mean the sequence xn is contained in A, and obviously xn is not equal to 1 for all n, and xn converges to 1, right? So we have a convergent sequence xn whose all the term is not equal to 1 and the xn is contained in A, and this xn converges to 1. Therefore 1 is a limit point of A. Therefore 1 is a limit point of A. Fine. So if we take that open interval 0, 1, then we have found that 0 is a limit point and 1 is a limit point. So is there any other limit point of this set? Of course. Even if we take any element from this set, so that point will be a limit point of A as well. So here we have two limit points 0 and 1. These are the limit points of A, and these limit points are not in A, right? But if we choose any elements from A, then we will now show that that point will also be a limit point of A, and that limit point is contained in A. So now we choose any point x belongs to A, that is open interval 0, 1. Okay. Now we claim that x, the point x, is a limit point of the set A. Okay, that's mean we have to find one sequence xn where each term of the sequence xn will be in A, and xn is not equal to x, and xn converges to x. Okay. So since 0 less than x, right? So by the Archimedean property we have there exists a natural number n such that 0 less than 1 by n less than x, right? Now if we define a sequence xn equal to say x minus 1 by say n plus that capital N, right? Then this sequence, the each term of this sequence belongs to A, right? For all n. And xn not equal to x, obviously, and xn converges to x. Therefore, x is a limit point of the set A. Now, what about the closedness? So, is the set A closed? No, right? Because the set A does not contain all of its limit point, because 0 and 1 are two limit points of A, but A does not contain those two limit points. Therefore, A is not closed. So, A is not a closed set because A, or you can write 0 and 1 are limit points of A, but the set A does not contain zero and 1. Okay. Now what about if we take the second example, say closed interval 0, 1. Okay. Now by similar argument as above, you can check that each element of A is a limit point, right? By the similar argument as above, you can check that 0 is a limit point, 1 is a limit point, and any element between 0 and 1 is also a limit point of the set A. Now, to prove that A is a closed set, you have to prove that A contains all of its limit points. That's mean A does not have any other limit point other than or outside the interval. So how to prove that? So what is my definition of a limit point? So you have to find one sequence xn, one convergent sequence xn, such that xn is not equal to x and xn converges to x, right? Now, so let xn be a arbitrary sequence in A. Okay, or arbitrary, you can write convergent sequence, arbitrary convergent sequence in A. Then 0 less than equal to xn less than equal to 1 for all n, right? Now if we apply the sandwich theorem for the sequence, then we will get, so by sandwich theorem for sequence, we will get 0 less than equal to limit of xn less than equal to 1, and this is my x, right? So that imply 0 less than x less than 1. Or here we write what is my x? X is the limit point of xn. Okay, so that's mean whenever we have a sequence, convergent sequence in A, then its limit should be in A as well. That imply limit of xn belongs to A as well, right? So therefore A contains all of its limit points, right? So A is closed. Thus A is closed. Fine. Now what about if we choose say A equal to some set like 1, 2, 3, that 3 element set, or say set of natural number, or the set of Z, set of integers. Okay, then what can we say about these sets? Now you can easily check that here. In this case, it is easy to check that any convergent sequence xn contained in A must be a eventually constant sequence. Right? You can easily check that by the definition of a sequence and by assuming epsilon equal to say half or 1 by 3. Fine? That's mean whenever you have a convergent sequence in A, then that sequence should be a constant sequence, or more precisely this is a eventually constant sequence. That's mean after some stage all the elements should be same, right? But what is the definition of a limit? The definition of a limit means we need a convergent sequence, right, where each term is not equal to x and xn will converge to x. But if my set A is this, then there will be no such sequence, right? So therefore A does not have any limit points. Since A does not have any limit points, in other words, you can say that A contains all of its limit points, right? So therefore, by default, A is closed. Okay? So now, this is the definition of limit of a set. Now, we are ready to define limit of a function. So right, limit of a function. So first of all, let A subset of R be any set. Okay, so A be any, you can write any non-empty set. Okay, and let a point A be a limit point of A. So for simplicity, you can assume A is a interval. Okay, so you can assume A as an interval, but this is true for any set. Okay, now let f A to R be a function. Okay, so note that to define the limit of a function at a point a, we need that small a should be a limit point of the set A. So in case of interval, we can choose any point of that interval, or we can choose the boundary values of the interval as well. But if A is not an interval, then you have to choose, to define the limit of a function, you have to choose a point which is a limit point of the set. You have to remember that. Okay, otherwise we cannot define the limit of a function. Now here A is any non-empty set and the point A is a limit point of the set A, and if A to R be a function. Now we say the limit of the function fx is L. L is a real number. Okay, L belongs to R. So we say the limit of the function fx is L as x approaches to A. Okay, and we write in this way that limit x tends to A, f of x equal to L. Okay, now when, so if for any sequence xn in A with xn not equal to A and xn converges to A, we have limit n tending to infinity f of xn equal to L. Now here you have to remember that whenever we choose a sequence, we have to choose this sequence must be in A. Okay, so this is one. Another thing is that sequence should not be A. So that sequence xn should be not equal to A. Okay, and xn converges to A. So why we can always choose this type of sequence? Because A is a limit point of the set, right? Since A is a limit point of the set capital A, so we can choose such a sequence xn in A such that xn not equal to A and xn converges to A. Now if for any arbitrary sequence in A we have, with this property, we have f of xn converges to L, then we will say that L is a limit of the function f at x equal to A, or we can say that x approaches to A. Now note that here L may not be equal to fa and the function may not be defined at the point A. So here you have to note that one as well. Here I can write note. So first of all, the function f may not be defined at A. That means f A may not be defined. Even if it is defined, if f of A is defined, f of A may not be equal to L. May not be equal to L. Since limit of a sequence is unique, therefore by the definition it follows that if limit of a function exists, then it must be unique. So we can write here it is. Okay, so that's mean suppose f is a function from a to r and we want to find the limit of the function f at x equal to say a. Now if we have two sequences, say xn goes to a and yn again goes to a, such that f of xn goes to l and f of yn goes to m, and if l not equal to m, then we say that the limit of the function f at x equal to a does not exist. Okay, therefore by the definition it follows that limit of a function must be unique. Now we shall see few examples. So first of all, we can take first example is say f is a function from R to R defined by f of x equal to say x square if x not equal to 2 and 1 if x equal to 2. Now since my domain is R, so any point in R is a limit point, right? Now suppose we want to find limit extending to 2 f of x. So what is this? Now we can prove this by our definition. First of all, let xn be a sequence. So this is an arbitrary sequence in R such that xn is not equal to 2 and xn converges to 2. Now by the algebra of the sequence we know that since xn goes to 2, that is xn converges to 2, therefore xn into xn, so xn square converges to 2 square, that is 4, right? So that implies f of xn converges to 4, and this is true for any arbitrary sequence xn such that xn converges to 2. So that is x converges to 2, f of x equal to 4 by the definition, right? Now note here limit x tending to 2 f of x equal to 4, and this is not equal to f of 2, right? So here the limit of f at x equal to 2 exists and it is not equal to the values of the function at that point, right? Now we can have another example, say if R2, or we can write it is say open interval 0 1 to say R, and f of x is just my, you can write just x. Okay, now note that here 0 and 1 are the boundary values of the open interval, and we have seen that those are the limit points, right? So therefore limit x tending to 0 f of x, this is well defined, right? So we can talk about the limit of the function at x equal to 0 or when x approaches to 0, right? Now what is this? Now here for any arbitrary sequence xn in 0 1 such that xn converges to 0, will imply f of xn converges to 0, right? So trivially we check that limit x tending to 0, f of x equal to 0. Now note that here the limit of the function f at x equal to 0 or as x approaches to 0 is equal to 0. But the values of the function at x equal to 0 is not defined. But f of 0 is not defined. Now we define two concepts of limit called limit at infinity and infinite limit. So here it is, limit at infinity. So first of all, let f be a function from a to infinity, that is the open interval a to infinity for some a to r. Okay, so this be a function. Then we say the limit of the function f function fx is L. Here this L is a real number. Okay, so we say the limit of f is L as x approaches to infinity, or you can say directly that at infinity, and we write as limit x tending to infinity f of x equal to L if for any sequence xn in that interval with xn diverges to infinity, or you can say that xn goes to infinity. So if for such a sequence we have limit n tending to infinity f of xn equal to L. So that's mean if we have a function f where the domain is some a to infinity, and if for any sequence xn where xn goes to infinity we have f of xn goes to L, then we say that the limit of the function f is L at infinity or as x approaches to infinity. Okay, now this is called the limit at infinity, that is the finite limit at infinity. Similarly, we can define limit at minus infinity as well. You can write it similarly. We can define limit at minus infinity. Okay. Now there is another concept called infinite limit. Infinite limit. Note that in our definition of limit, this one, limit of a function, we assume that x belongs to R, right? So x is a real number. Now here we define in such a way that L can be infinity as well. So we can write here, let a subset of R be any set for simplicity, you can assume A equal to an interval, say A, B, open interval A, comma B. Okay, but in fact you can choose any set. So let this A, that capital A, be any set, and that small a be a limit point of the set A. Okay, and let f this A to R be a function. Now we define the limit of the function f is infinity. Okay, so instead of L we are writing infinity as x approaches to the point A, or you can say the limit is infinity at x equal to A, and we write limit x tending to A f of x equal to infinity if for any sequence xn in A with each term of the sequence xn is not equal to A and xn converges to A, we have f of xn goes to infinity, or you can say f of xn diverges to infinity. So then we say that the limit of the function f is infinity at x equal to A, or when x approaches to A. Now we shall see few examples. So first one, we can take f is a function from r minus 0 to r defined by f of x equal to 1 by x, and we wish to find limit x tending to 0 f of x. Okay, so we want to find that the limit does not exist or the limit is infinite. Okay, so we will check that. Now first of all, if you take xn equal to 1 by n, right, then what is my f of xn? F of xn equal to n, right? So here xn converges to 0 and f of xn diverges to infinity or goes to infinity, right? But if you take another sequence, say yn equal to say minus 1 by n, then f of xn equal to minus n, right? Now here again yn goes to 0, but my f of yn goes to minus infinity. So that's mean here we cannot say that the limit is infinite, right? Because whenever we can choose two sequences xn and yn, but for those two sequences they are converging to 0, but when we take f of xn, that converges to infinity, and if we take f of yn, so it converges to minus infinity, right? So therefore here, since f of xn and f of yn has different limit, so we can say that by our definition, limit x tending to 0 f of x does not exist. Now what if if my function is the same one, say f r minus 0 to r, okay, and suppose f of x equal to 1 by x square. So instead of 1 by x, we write f of x equal to 1 by x square. Then what will be my limit x tending to 0 f of x. Now here you can check that limit exists and it is infinite. Limit exists means that infinite limit exists. Okay. So here we can prove it. So for any sequence xn in r minus 0 with xn converges to 0. Now since xn converges to 0, that implies xn square is also converges to 0 and all of these terms are positive, right? Now that implies 1 by xn square converges to or diverges to infinite, right? Or you can say 1 by xn square goes to infinite as n goes to infinite. Now that implies limit n goes to infinite f of xn equal to infinite, or you can say f of xn diverges to infinite, right? Now here the infinite limit of xn of the function f exists at x equal to 0. Now here we have infinite limit. So here we write limit x tending to 0 f of x equal to infinite. Now this is the difference between the infinite limit and the limit does not exist. Okay. Now let's refine this example a little bit. Say example 3. F is a function from again r minus 0 to r, okay, and defined by f of x equal to sine 1 by x square, and we wish to find limit x tending to 0 f of x. Okay. Now here is the solution. So let xn equal to 1 by root over 2 pi n and yn equal to 1 by root over 2 pi n plus pi by 2. Now why I choose this type of sequences? Because so in that case my xn we know that is converges to 0 and yn converges to 0. But what is my f of xn? Now f of xn is sine of 2 pi n, right? Since f of x equal to sine 1 by x square. So sine 2 pi n and that is 0. So this is converges to 0. And f of yn equal to sine 2n pi plus pi by 2 and that is 1 and that is converges to 1. So therefore we have two sequences and both of them converge to 0, but f of xn converges to 0 and f of yn converges to 1. So therefore they have different limit. So we can say that the limit x tending to 0 f of x does not exist, right? So whenever we will have two sequences for which f of xn and f of xyn will have different limits, in that case we shall say that the limit at that point or limit of the function at that point does not exist. Now again if we refine this example, say again if r minus 0 to r be a function defined by f of x equal to x sine 1 by x square, and we wish to find again limit x tending to 0 f of x. Now we prove that this limit exists. Why? Now first of all check that we know that sine of any value lies between -1 and 1, right? So -1 less than equal to sine 1 by x square less than equal to 1 for all x, right? Belongs to that r minus 0. Now see here we cannot multiply x on these three sides because x can be negative. So therefore we will write this is as say mod of sine 1 by x square, that is less than equal to 1, or you can write this is less than equal to x, right? Greater equal to 0. So we can write it is 0 less than equal to mod of x sine 1 by x square, and that is less than equal to mod of x. Okay. Now if we choose a xn is a sequence in r minus 0 such that xn converts to 0. So we choose xn is a arbitrary sequence which converts to 0, right? Now that imply 0 less than equal to mod of xn sine 1 by xn square, that is less than equal to again mod of xn, right? That imply 0 less than equal to mod of f of xn less than equal to mod of xn. Okay. Now we know that xn goes to 0, so therefore this is goes to 0. So by the sandwich theorem for sequence we have limit, that is f of xn also converts to 0. Now since mod of xn converts to 0 as n tending to infinity, we have f of xn, or first we write f of mod of f of xn converts to 0 as n tending to infinity, that is f of xn converts to 0 as n tending to infinity. Therefore that limit f of x that is 0. So limit exists. Okay. So now look at a different type of example. Now say f is a function from R to R defined by such that f of x equal to box of x. So what is this? Sometimes we write it is in this way, that is floor of x. So what is this? So box of x or floor of x, that is it is the greatest integer value less than equal to x. Okay. So therefore in other words f of x equal to n if n less than equal to x strictly less than n plus 1, okay, where n belongs to z. And suppose we wish to find limit x tending to 1 f of x. Okay. Now here is the solution. So first of all, if we choose, say, the sequence xn equal to 1 plus 1 by n plus 1, okay, then obviously that xn converts to 1, right? That's when n tending to infinity. Now what is my box of xn? So that is the greatest integer less than equal to x, less than equal to xn, right? So this will be my 1, right? So this is my f of xn equal to this, and this is converts to, since it is singleton 1, so it is converts to 1 as n tending to infinity, right? Now if we choose, say, yn equal to that 1 minus 1 by n plus 1, then again yn converts to 1 as n tending to infinity. But what will be my f of yn? Now f of yn will be that box of yn, that is the greatest integer less than or equal to yn, right? Now that will be, you can check, that will be 0, right? Because this number, that is that yn, is always bigger or equal to 0 but strictly less than 1, and that is, since this is a constant sequence, so this is converts to 0 as n tending to infinity, right? So therefore we have two sequences xn and yn, both of them converts to 1, but f of xn converts to 1 and f of yn converts to 0. Therefore limit x tending to 1, f of x does not exist. Okay. Now note that here in this case, if we choose any sequence xn which is bigger than x but converts to 1, then for that sequence, if xn converts to 1, then f of xn converts to 1, right? So that f of xn has a limit. And if we choose any yn such that yn is less than 1 and yn converts to 1, okay, then f of yn has also a limit, right? But if we have the combination of both of them, then that sequence do not have a limit, right? Now inspired by this, we will define another notation or another definition which is called one-sided limit. Okay, so here is my one definition called one-sided limit. So we shall define this limit, okay, and then again we came back to this example. So first of all, suppose we want to define that one-sided limit at a point C. Now for simplicity, first of all we can write this one. So for simplicity, just assume f is a real valued function which is defined on an open interval, say C, D. Okay. So for some that C, D belongs to R. Okay. Now if f is a function or real valued function which is defined on a open interval C, D, then we can talk about the right hand limit at C. Now then the right hand limit of the function f of x at x equal to the point C is L if for any sequence xn in the interval that c comma d such that xn converts to c implies f of xn converts to L. That's mean we take any arbitrary sequence xn which converts to c, but all of this term of the sequence is bigger than c. Okay. Now if for all such a sequence which converts to c and bigger than c, if f of xn converts to L, then we say that the right hand limit of f of the function fx at x equal to c is L. Now similarly we can define the left hand limit as well, and in this case we denote, or you can say we write the limit extending to c plus means the right hand limit at c f of x equal to L. Now similarly we can define the left hand limit, right? Now let f be a real valued function defined on a open interval, say b comma c. Okay, so for some b comma c belongs to R. Now then we define the left hand limit of f of x at x equal to c is L if for any sequence xn in the open interval b comma c with f xn converts to c implies f of xn converts to L. So when we talk about the sequence converts to some point, then we always assume that n tending to infinity, right? But sometimes I skip that part, that n tending to infinity, but you have to remember that whenever we say that xn converts to c or f of xn converts to L, so by default n tending to infinity, but sometimes I miss this one. Okay, and in this case we write that limit extending to c minus f of x equal to L. So c minus means left hand limit. Okay, that's mean the limit of the function f, okay, the limit, that is the left hand limit of the function f at x equal to c is L. Okay, so now this is the definition of one-sided limits. Now again we back to the previous example, this one. So let f of x equal to, that is that box x, and f is defined from R to R. It is better to write first, right? So f R to R be a function defined by f of x equal to box x. Now we have already seen that limit extending to 1, in fact limit extending to any integer, f of x does not exist. But now here we wish to find limit x tending to n plus f of x and limit x tending to n minus f of x for n belongs to integer. Okay. Now here is the solution. So first of all, we just write the function. So this is the function f of x equal to, that will be n if n less than equal to x strictly less than n plus 1 for all n belongs to z. Okay. So now let this n belongs to z. Okay. So now let x say m belongs to the interval n comma n plus 1, that open interval this. Here my c is n and d is n plus 1. So this be such that xm converts to n. So here n is arbitrary integer but fixed, okay, and xm is the integer, that is xm is the sequence. So as m tending to infinity. Okay. Now xm is a real number belongs to the interval n comma n plus 1. So f of xm, which is box of xm, that is just n, right? So this is converts to n as m tending to infinity. Here xm is a arbitrary sequence, right? So whenever we have an arbitrary sequence xm such that xm converts to n, then f of xn converts to n, right? And if we choose that xm is bigger than n. So therefore, by definition, the right hand limit, so limit x tending to n plus f of x will be n. Now let ym be a sequence in n minus 1 comma n. So this is my b and this is my c, and here this was my c and this was my d. Okay. Now let be a sequence such that ym converts to n as m tending to infinity. Now by the definition, what is my f of ym? Now if we choose any arbitrary sequence ym which is in this interval and ym converts to n, then f of ym will be my box of ym. So by definition this will be n minus 1, right? So this is a constant sequence. So this is converts to n minus 1 as m tending to infinity, right? Now since this sequence ym is arbitrary, so we can write limit x tending to n minus, that is the left hand limit of f of x equal to n minus 1. Okay, so I stop here today. In the next lecture I shall continue from this. So in the next lecture I shall start with one theorem which states that the limit of a function at a point exists if and only if its left hand limit and the right hand limit both exist and both are equal. So provided they are well defined. Okay. So see you in the next lecture.